What if the oldest stories we ever told were not written in stone but in ice? What if the most profound prophecies were not spoken by mortals but were etched in dust and gas, carried across impossible voids on journeys lasting millions of years? For as long as we have looked up, they have been there. The silent visitors, the celestial ghosts, comets. To our ancestors, they were a terrifying and beautiful paradox, a tear in the velvet fabric of the predictable night. They arrived without warning, their ethereal tales painting the heavens with luminous, unknowable script. They were the harbingers of doom, the divine messengers, the swords of God hanging over the world. When Halley's comet blazed across the sky in 1066, it was woven into the Bayeux tapestry not as an astronomical event, but as a divine omen foretelling the fall of a king and the violent birth of a New England. For centuries, their appearance was tied inextricably to our own fate on Earth, their ghostly light casting long shadows over the greatest triumphs and deepest tragedies of human history. They were celestial arbiters, their presence a source of profound dread and sacred awe. We now know they are not gods, nor are they demons. They are something far more mysterious and infinitely more profound. They are time capsules, pristine relics from the violent, chaotic dawn of our solar system, born more than 4.5 billion years ago. They are the leftover building materials, the primordial rubble from which the planets were forged. Locked within their frozen hearts are the original chemical ingredients of our cosmic neighborhood: water, carbon-complex organic molecules, the very seeds of life itself. These celestial nomads spend the vast majority of their existence in a state of deep frozen slumber, orbiting silently in the cold, dark abyss of the outer solar system, far beyond the most distant planets in a vast theoretical sphere of icy bodies we call the Oort Cloud. They are ghosts in the truest sense, unseen, unheard, their existence a quiet whisper in the cosmic dark. But sometimes a subtle gravitational nudge, a gentle push from a passing star, or a jostle from a fellow wanderer is all it takes. A single comet is dislodged from its ancient stable orbit and begins a long, slow, inexorable fall inward toward the heart of the system, toward the sun. As it journeys closer, the sun's warmth begins to stir the sleeper from its multi-million-year dream. The ice, frozen harder than granite for eons, begins to sublimate, turning directly into gas. This process, a gentle celestial sigh at first, grows into a furious exhalation, enshrouding the comet's solid nucleus in a vast, glowing atmosphere called a coma. This cloud of gas and dust, often growing larger than the planet Jupiter, becomes a canvas for the sun's light. Solar radiation energizes the gases, causing them to glow with an otherworldly luminescence, while the solar wind, a constant stream of charged particles flowing from the sun, pushes this material away, sculpting it into the two magnificent tails we see from Earth, a bright, curved dust tail and a straighter, fainter ion tail that points directly away from our star. Each comet that graces our sky is therefore a unique performance, a one-time cosmic spectacle. It is a living object interacting with its environment, changing day by day as it endures the sun's relentless energy. And for those of us who watch from the distant shores of Earth, the arrival of a new bright comet is a moment of shared wonder, a connection to the raw, untamed nature of the cosmos. It reminds us that our solar system is not a static clockwork machine, but a dynamic living place filled with wild, untamed beauty. Recently, the astronomical world began to buzz with just such a promise. A new visitor was inbound, a traveler from the deep dark named Comet 3I, Atlas. Discovered by the Asteroid Terrestrial Impact Last Alert system in the final days of 2019, Atlas was from the very beginning special. Its trajectory was a thing of mathematical beauty and terrifying potential, a hyperbolic path that meant it was not a returning visitor, but a pristine first-time guest from the Oort Cloud. These virgin comets are the most unpredictable, their surfaces having never before felt the warmth of a star. As it plunged toward the inner solar system, it began to brighten at a truly astonishing rate, far exceeding all predictions. Week after week, its magnitude surged. Astronomers and amateur stargazers alike watched in breathless anticipation. The calculations were exhilarating. By the time it reached its closest approach to the sun, Atlas was projected to become a magnificent spectacle, potentially bright enough to be seen with the naked eye even in twilight skies, its tail stretching like a celestial brushstroke across the vault of heaven. It was being hailed as the potential comet of a generation, a once-in-a-lifetime visitor that would unite the world in a shared moment of cosmic awe. It was a story of pure, unadulterated hope, a gift from the cosmos, arriving just when we needed it most. But the universe is rarely so simple. Its grandest promises are often wrapped in the most profound mysteries. As Atlas continued its journey, something strange began to happen. The furious exponential brightening that had so captivated us began to slow, then sputter, then stall completely. The light curve, the measure of its brightness over time, which had been a steep, thrilling climb, suddenly flattened out. It was like watching a sprinter leading the race suddenly falter and lose their stride. Confusion rippled through the scientific community. Was it simply outgassing in a strange, non-linear way, or was this a symptom of something far more serious? A sign of a deep structural instability within the comet itself? The answer, when it came, was both spectacular and heartbreaking. Through the unblinking eyes of our most powerful telescopes, we saw the truth. Comet Atlas was dying. The immense gravitational forces of the Sun, coupled with the violent explosive outgassing from its own heating core, were proving too much. The primordial glue holding its icy heart together was failing. It wasn't just fading away. It was disintegrating. The Hubble Space Telescope was turned toward the fading visitor, and what it revealed was not the single brilliant point of light we had hoped for, but a ghostly, elongated smear. Over the following days, Hubble's follow-up observations were even more stark. Atlas had shattered into a cascade of smaller, fainter pieces. The images showed dozens of icy fragments, each now on its own, slightly different path, continuing the journey like a silent, ghostly funeral procession. The great comet that was supposed to light up our skies had become a string of cosmic debris, a trail of celestial breadcrumbs marking the path of a spectacular failure. The dream was over. Instead of a celebration, we were left with a profound scientific puzzle. Why did it break apart? Was it a structural flaw, a weakness inherent in its composition from the day it was formed billions of years ago? Or did all first-time visitors from the Oort Cloud face this crucible with only the strongest, surviving their first fiery pass around the Sun? The death of Atlas left a void not just in our skies, but in our understanding. It was a stark reminder that these celestial visitors are not just beautiful objects, but fragile travelers on a perilous journey. The Sun, which gives them their glorious light, is also their executioner. It is a celestial blowtorch that can either reveal their inner beauty or shatter them into dust. And then, just as the ghost of Atlas began to fade into memory, another whisper came from the darkness. In the spring of 2020, an amateur astronomer named Michael Mattiazzo was poring over publicly available data from a NASA instrument called SWAN, the Solar Wind Anisotropies instrument, aboard the SOHO spacecraft. SWAN's purpose isn't to find comets. It's designed to scan the entire sky in ultraviolet light, mapping the flow of hydrogen across the solar system. Comets, as they release vast quantities of water, create enormous clouds of hydrogen atoms around them, clouds that are invisible to the human eye but blaze brightly in SWAN's ultraviolet view. And there in the data, Mattiazzo spotted a huge, unexpected surge of hydrogen. A new comet missed by all the major automated surveys had been quietly creeping into the inner solar system. It was designated C 2020 F8, but it would forever be known by the name of the instrument that revealed its presence, Comet SWAN. Almost immediately, the parallels were uncanny, almost unnerving. Like Atlas Comet, SWAN began to brighten at a spectacular, almost violent rate. Its light curve started to trace a trajectory hauntingly similar to the one that had preceded the catastrophic collapse of its predecessor. It too was on an orbit that suggested it might be a pristine visitor from the Oort Cloud, a fragile newcomer unaccustomed to the harsh environment near the Sun. And as it drew closer, it developed a stunningly beautiful intricate tail and a vibrant green coma, the telltale glow of diatomic carbon being energized by solar radiation, the exact same verdant hue that had made Atlas look so promising in its early days. The astronomical community watched with a sense of cosmic déjà vu, a feeling of both excitement and trepidation. Was this a second chance? A cosmic redemption giving us the spectacular show that Atlas had promised but failed to deliver? Or were we doomed to watch a horrifying replay, another story of celestial hope destined to end in fragmentation, dust? The mystery only deepened as we learned more about this new interloper. Comet SWAN was in many ways an even more extreme object than Atlas. The hydrogen cloud that SWAN had detected was immense, stretching across millions of miles of space, indicating a truly prodigious rate of water sublimation. This comet was not just outgassing, it was hemorrhaging material. It was this furious activity that was making it so brilliantly bright, so unexpectedly beautiful. But this same frantic activity is also a hallmark of structural instability. It's like a fire burning too hot too fast, spectacular for a moment, but destined to consume its fuel and burn out quickly. Every beautiful image of SWAN carried with it a double meaning. The very brilliance that made it so captivating could also be the signature of its impending doom. It was a celestial paradox, a breathtaking object living on a knife's edge between glory and self-destruction. The ghost of Atlas loomed large over every new observation, a cautionary tale whispered from the void. Every data point was scrutinized, every change in brightness analyzed for the first subtle signs of the same sickness that had claimed the last great hope. And now these two cosmic stories, one of a spectacular death and the other of a precarious new life, are beginning to converge in a truly extraordinary way. Their orbits, while different, have brought their stories into a dramatic celestial alignment with our own planet. As you watch this, the scattered, fading fragments of what was once Comet Atlas are continuing on their path, a silent debris field passing on one side of Earth's orbit. At the same time, the brilliant, volatile new challenger Comet SWAN is charging inward its trajectory, bringing it close on the other side. For a brief moment in cosmic time, our world is being flanked by these two comets caught in the middle of a silent, unfolding drama. We are witnesses to a cosmic echo, a story being told in two parts across the vastness of space. On one side, the tragic conclusion. On the other, the uncertain, suspenseful beginning. It is a celestial pincer movement of past and future, of failed promise and fragile hope. This extraordinary alignment forces us to ask a much deeper, more tantalizing question. Is this all just a grand coincidence? Is it simply by chance that two comets, both potentially pristine visitors from the Oort Cloud, would arrive in our skies in quick succession, exhibit the same volatile behavior, and trace such similar arcs of brilliant hope and potential disaster? Or are we seeing something more? Could Comet Atlas and Comet SWAN be related? Is it possible that they are not two separate strangers, but long-lost siblings, two fragments of a much larger, more ancient parent comet that broke apart thousands or even hundreds of thousands of years ago, far out in the frozen darkness? If so, we are not just watching a comet, we are uncovering a family history written in ice and light, witnessing the final act of a cataclysm that began before human civilization was even born. The story of SWAN is no longer just about whether it will survive. It has become a detective story, a forensic investigation into a primordial crime scene, with the fate of Atlas as the crucial piece of evidence and the survival of SWAN as the final dramatic verdict. We are now on a journey following this icy wanderer as it makes its most perilous passage. We will travel with it as it approaches perihelion, its closest and most dangerous encounter with the Sun. We will watch using the combined power of observatories around the world and in space for the telltale signs that will determine its fate. Will its nucleus hold together under the immense strain? Will its light curve continue to climb, heralding the arrival of a truly great comet? Or will we see the first subtle signs of faltering, the same ghostly quiet that preceded the fall of Atlas? We stand on the cusp of a great cosmic phrasic revelation. The sun-forged crucible is waiting. The forces that will determine SWAN's destiny are already at work, a silent, titanic struggle between the comet's primordial strength and the star's relentless power. And we, on our small blue world, caught between the ghost of what was and the hope of what could be, can only watch and wait. The question is no longer times. If times, we will see a spectacle, but what kind? It will be a radiant coronation or a silent, spectacular death. What if you could hold a piece of creation in your hand, not a rock, not a fossil, but an intact message from the very dawn of our solar system, a time before planets, before worlds, before even the faintest possibility of us? What if this messenger, after a 4.5 billion year sleep in the deepest, coldest vaults of space, finally awoke and began a journey of 1,000,000 years just to pass by our window? These are not fantasies. They are comets. And they are some of the most profound, enigmatic, and dangerously unpredictable objects the cosmos has ever sent our way. To understand the drama now unfolding in our skies, to grasp the ghostly echo we are seeing in a new visitor named SWAN, we must first journey back to the source. We must travel to the great dark kingdoms of ice that lie at the forgotten edges of our sun's domain. Imagine our solar system not as the familiar clockwork of 8 planets, but as a vast and layered empire. Out here, far beyond the orbit of Neptune, beyond the lonely paths of the dwarf worlds, you enter a different reality. This is the Kuiper Belt, a sprawling icy junkyard of primordial leftovers. It's a flattened, donut-shaped ring of material that never quite managed to coalesce into a planet, a realm of perpetual twilight where sunlight is weaker than the brightest moon in our sky. Here, trillions of frozen bodies drift in a slow, majestic dance, locked in a state of arrested development. They are the building blocks of worlds that never were composed of the same raw dust and ice that formed Earth, Jupiter, and all the others. For billions of years, they have circled in relative stability, their stories unwritten, their potential locked away in a deep freeze. This is the nursery for a specific class of cosmic wanderer, the short-period comets, those visitors who return to our skies every few decades or centuries, their orbits tamed and bound by the gravity of our system's giant planets. But to find the true titans, the long-shot visitors that appear only once in recorded history, we must travel further still, much, much further. We must leave the Kuiper Belt behind and plunge into an abyss of unimaginable scale. Out here, 1,000 times more distant than Pluto, the sun's gravitational grip becomes so tenuous it is barely a whisper. You have arrived in the Oort Cloud. It isn't a belt or a ring, it is a ghost, a colossal spherical shell of perhaps 1 trillion icy nuclei that completely envelops our entire solar system. This is the deep archive, the outermost wall of our sun's empire. The objects here are so far apart that if you were standing on one, you would likely never see another. The darkness is absolute, the cold so profound that atoms themselves slow to a crawl. These are the true relics hurled out into this cosmic purgatory during the violent, chaotic youth of the solar system, when giant planets migrated and threw their smaller siblings into these impossibly distant orbits. They wait there in the stillness, silent for eons, orbiting so slowly that a single year might last for 30 million of our own. They are perfectly preserved time capsules, their chemistry unchanged since the moment of their birth. But their slumber is not eternal. The galaxy is not an empty place. Out in this great darkness, the subtle gravitational pull of a passing star, a wanderer from another system, can act as a cosmic finger flicking one of these sleeping giants out of its stable orbit. Or the slow, collective tidal force of the Milky Way itself can gently perturb its path. That is all it takes. A nudge imperceptible to us but cosmically decisive, and with that a new journey begins. A slow, patient fall inward, a 1,000,000-year descent from the ghostly frontier toward the fire at the heart of the system. This object, which has known only absolute cold and darkness, is now on a collision course with the Sun. As it crosses the orbit of Neptune and then Uranus and Saturn, the world it enters grows increasingly hostile. What was once a faint, distant star now swells into a blazing disk. For the first time in its existence, the comet begins to feel warmth, and this warmth is the trigger for one of the most beautiful and violent transformations in nature. The nucleus of a comet is often described as a dirty snowball, but that simple phrase belies its true complex nature. It is a fragile conglomerate of water, ice, dust, and rock, all loosely bound together. Yet mixed within this matrix are far more volatile substances: frozen carbon dioxide, methane, ammonia, and carbon monoxide. These are gases that boil at incredibly low temperatures. As the sun's energy touches them, they do not melt. They sublimate, turning directly from solid ice into gas. This process begins to form a vast, glowing atmosphere around the solid nucleus, an ethereal shroud we call the coma. This cloud of gas and dust can swell to become larger than the planet Jupiter, a temporary self-generated world of stunning beauty. The solar wind, a constant stream of charged particles flowing from the sun, then pushes this material away, sculpting it into the iconic tails. There is the bright, curving dust tail composed of tiny solid particles reflecting sunlight, and the dimmer, straighter ion tail made of glowing gases pushed directly away from the sun by its magnetic field. The comet is no longer a sleeping rock. It has become a spectacle. It is alive, a celestial creature, breathing fire and light as it hurtles through the inner solar system, its tail stretching for tens of millions of miles behind it, a temporary banner painted across the night sky. For those of us on Earth, witnessing the arrival of a great comet is a primal experience, a connection to a universe far older and grander than ourselves. It is a promise of a once-in-a-lifetime show. And in late 2019, just such a promise was made. It was discovered by a robotic survey in Hawaii, the Asteroid Terrestrial Impact Last Alert System, or ATLAS. The designation it received was C, 2019Y4, but it would forever be known by the name of its discoverer. To astronomers, it was Comet Atlas. At first, it was just another faint smudge among millions, a minor point of data destined for an obscure catalogue. But then something remarkable began to happen. As Atlas journeyed inward past the orbit of Mars, it began to brighten. And not just brighten, but surge in luminosity at a staggering, almost unprecedented rate. The numbers were intoxicating. Calculations showed that if it continued on this trajectory, by the time it made its closest approach to the Sun in May of 2020, it could become brilliantly visible to the naked eye, perhaps even rivaling the planet Venus in the twilight sky. It had the potential to be a generational comet, the kind of spectacle that grandparents tell their grandchildren about. The world took notice. In a time of growing uncertainty on Earth, this visitor from the outer dark became a symbol of cosmic hope, a shared global event that we could all look up and witness together. Stargazers dusted off their telescopes. The media breathlessly reported on its progress. Every new image showed it growing larger, its green-tinged coma glowing with an otherworldly light. It was on the perfect trajectory, a path that would swing it tantalizingly close to the Sun and then bring it into prime viewing position for the Northern Hemisphere. It seemed too good to be true, a perfect celestial performance delivered on cue. This was the dream of every astronomer and every casual skywatcher, a bright, beautiful, and predictable comet. But the universe rarely deals in such simple certainties. Comets, these ancient messengers, carry within them not just the secrets of creation, but also the seeds of their own destruction. Their beauty is born of their own self-immolation, and that process is fundamentally violently unstable. In late March of 2020, just as the anticipation was reaching its peak, the first whispers of trouble began to circulate. Seasoned observers noted that the comet's brightening had stalled. Then it seemed to be dimming. The sharp star-like point of light at its core, the pseudo-nucleus, appeared to be elongating, becoming fuzzy and indistinct. Something was wrong. The celestial superstar was faltering. The great observatories of the world turned their gaze upon the ailing comet, trying to diagnose its condition from hundreds of millions of miles away. It was the Hubble Space Telescope that delivered the final, devastating verdict. Its impeccably sharp vision sliced through the glowing coma and revealed the truth. The nucleus of Comet Atlas was no longer a single solid body. It had shattered. Hubble's images were both heartbreaking and scientifically riveting. They showed not one object, but a cascade of smaller, icy fragments, a string of cosmic pearls drifting apart in the darkness. Over the coming days, astronomers watched in morbid fascination as these pieces themselves continued to break apart, crumbling into smaller and smaller bits. The comet was not just fizzling out. It was undergoing a complete and catastrophic structural failure. It was disintegrating before our very eyes. The great show was over before it had even truly begun. Within weeks, the once promising celestial beacon had faded into a faint, ghostly smear, a diffuse cloud of debris continuing on the same path, a funeral procession marking the spot where a comet used to be. The hope that had united so many turned into a collective, quiet disappointment. But for scientists, the death of Atlas was not an ending. It was a beginning. It was a spectacular real-time lesson in the brutal physics of comets. What had happened? Why did it fall apart? The theories are numerous, each painting a picture of a body at war with itself. Perhaps the nucleus was a rubble pile, a very loosely bound collection of smaller ice chunks that simply couldn't withstand the growing thermal stresses as it neared the sun. As the volatile ices sublimated, they may have done so unevenly, creating jets of gas that torqued the nucleus, spinning it faster and faster until centrifugal force tore it to pieces, a gravitational gyroscope spinning out of control. Or perhaps its internal structure was simply too fragile, its icy bonds too weak to hold against the sun's relentless thermal assault. It was in essence a piece of celestial dynamite with a very short fuse, and its journey into the warmth of the inner solar system had finally lit that fuse. The legacy of Atlas is therefore a profound and cautionary one. It taught us more dramatically than any comet in recent memory that we cannot take these visitors for granted. They are not solid, predictable rocks like asteroids. They are fragile, volatile relics from the edge of chaos. Their brilliance is a direct measure of their instability. The very process that makes them beautiful, the sublimation of their ancient ices, is also the engine of their potential demise. A comet's journey toward the sun is a tightrope walk over a furnace. Some make it across. Many, like Atlas, do not. They are a gamble, a roll of the cosmic dice, and the spectacular failure of Atlas reset our expectations. It left behind a trail of unanswered questions about the inner lives of these icy ghosts, about the breaking point between spectacle and self-destruction. It became the new benchmark for unpredictability, the ghost in the machine of cometary science. It is a ghost that now appears to have a haunting new echo, because the universe, it seems, is not done with its lessons. As the dust of Atlas settled, another visitor discovered by a different sentinel, the Solar and Heliospheric Observatory's SWAN instrument, began its own journey inward. It too began to brighten with surprising speed. It too showed the telltale green glow of a gassy active comet. And it too is following a perilous path, a trajectory that puts it on a collision course with the same solar energies that proved fatal for its predecessor. We now watch this new player on the celestial stage, and we do so with a sense of cosmic déjà vu, armed with the fresh and humbling memory of a superstar that crumbled into dust. The questions that Atlas left in its wake now hang over this new arrival. Is it made of sterner stuff? Or is it another fragile time capsule destined to put on a brilliant, fleeting show before shattering under the strain? We are watching a story we think we have seen before, a drama of cosmic promise and inherent peril. And this time the comet is flanking Earth, and so the stage stood empty. The ghost of Atlas, a fragmented whisper of dust and ice, had dissolved back into the void from which it came, leaving behind a profound silence in our skies. A sense of anticlimax lingered in observatories and backyards, a shared, unspoken disappointment for a celestial spectacle that had promised so much only to vanish at the final curtain. But the cosmos, in its infinite and patient grandeur, abhors a vacuum both in space and in our expectations. Even as the last echoes of Atlas faded from our telescopes, a new signal, impossibly faint, was already being written into the data streams of a machine built for a different purpose. It was a message not from the depths of interstellar space, but from our own solar system's sprawling frozen frontier. This story begins not with an eye pressed to a lens, but with the silent, ceaseless vigil of a solar sentinel. The Solar and Heliospheric Observatory, or SOHO, is a spacecraft forever staring into the incandescent heart of our sun, a collaboration between NASA and the European Space Agency. Its mission is to monitor the sun's volatile moods, to watch for the colossal eruptions and magnetic tempests that can buffet our world. Yet one of its instruments, a device named SWAN, possesses a unique and almost accidental secondary talent. SWAN stands for Solar Wind Anisotropies. It isn't a camera in the traditional sense. It sees the universe in a specific wavelength of ultraviolet light, the Lyman alpha line. This is the spectral fingerprint of hydrogen gas. SWAN's primary job is to map the entire sky for this signature, tracking how the torrent of charged particles from the sun, the solar wind, interacts with the sparse hydrogen atoms drifting between the planets. But comets, these ancient travelers from the Oort Cloud, are essentially dirty snowballs shedding vast clouds of gas as they warm up, and the most abundant element in that vaporous shroud is hydrogen. To SWAN, a comet approaching the Sun doesn't look like a bright point of light. It appears as a ghostly expanding blotch of hydrogen, a slowly growing anomaly in its all-sky map of the solar wind. It is a subtle disturbance easily lost in the noise of a star's fury. For weeks, from late March into early April of 2020, a new blotch had been steadily, almost imperceptibly growing. It was a celestial whisper, too quiet for automated systems to flag a secret waiting for a human mind to uncover. That mind belonged to Michael Mattiazzo, an amateur astronomer in Australia. He is part of a dedicated global community of comet hunters, citizen scientists, who sift through the public data from missions like SOHO, poring over images that professional astronomers focused on primary mission goals might overlook. It is a painstaking, often thankless search. Days turn into weeks of staring at grainy monochrome images, looking for the slightest smudge that moves against the background of fixed stars. On April 11th, navigating the archived data from SWAN, Mattiazzo saw it, a faint, diffuse patch of light, blossoming in the constellation of Grus. He meticulously cross-referenced its position over several days, watching it crawl with the slow, deliberate pace of a distant object falling under the Sun's immense gravitational command. This was no sensor artifact, no solar flare's lingering echo. It was real. It was moving. It was a comet. He submitted his findings to the Minor Planet Center, the official clearinghouse for all such discoveries, the astronomical community still nursing its wounds from Atlas, stirred with a tentative, cautious curiosity. Alerts flashed across the globe. In the high deserts of Chile, robotic telescopes of the Atlas survey, the very program that found its ill-fated namesake, swung their massive mirrors to the designated coordinates. In Arizona, the Catalina Sky Survey reoriented its search patterns. Networks of smaller university-run and amateur-owned observatories roused themselves from other duties to join the chase. The first optical confirmations trickled in, and with them, the first jolt of adrenaline. The object was there exactly where Mattiazzo predicted. It was designated C 2020 F8 SWAN, honouring both the instrument and the year of its discovery, and it was already brighter than it had any right to be. Most comets discovered at such a distance are little more than faint asteroidal points of light, their activity just beginning to stir. But SWAN was different. It already sported a magnificent, well-developed coma, a vast greenish atmosphere of sublimating gas tens of thousands of kilometers across. Even more strikingly, it displayed a long, delicate and highly structured ion tail, a streamer of charged particles being blown back by the solar wind. This level of activity, this pronounced and beautiful architecture, is typically reserved for comets much closer to the Sun. It suggested that SWAN was an unusually volatile and productive object, a celestial engine already running at full throttle. The initial calculations of its magnitude, a measure of its brightness, sent a current of genuine excitement through the community. It was brightening at a startling rate far faster than a typical comet. Every new observation seemed to add another layer of potential, another reason to hope that this was not just another faint smudge, but the cosmic spectacle we had been denied. With every observation from every point on Earth, astronomers were gathering crucial data points called astrometry, the precise measurement of the comet's position against the backdrop of stars. Each data point is a single breadcrumb on its celestial trail. A handful of them give you a rough guess of its path. Dozens from observatories separated by continents and oceans allow you to trace its orbit with breathtaking precision. The world's computers went to work crunching the numbers through the laws of gravity, extending the comet's trajectory forward in time. The result was astonishing. Comet SWAN was not on a path to intersect Earth's orbit, nor was it on a trajectory that would take it far away into the celestial periphery. It was doing something far more intimate and far more dramatic. It was set to execute a perfect flanking maneuver. Imagine two soldiers advancing on a parallel course. One is Earth moving in its familiar near-circular path around the Sun. The other is SWAN plunging inward from the outer dark on a vast parabolic curve. In the late days of May, their paths would draw incredibly close, not in a way that risked collision, but in a way that offered the most spectacular and sustained celestial flyby in recent memory. For weeks, the comet would not simply pass by in a single night. Instead, it would travel alongside us, a fellow mariner, on the solar sea. At its closest approach, it would be just over 80 million kilometers away, a cosmically trivial distance. From our moving vantage point on Earth, it would appear to race through our northern skies, a glorious, ghostly apparition visible with the naked eye from dusk until dawn. This orbital alignment was a geometric gift. It meant we wouldn't just get a fleeting glimpse. We would have a ringside seat, a prolonged encounter, allowing us to watch the comet evolve in real time as it made its perilous journey toward the Sun. The phrase flanking Earth began to spread a term that captured the strategic, almost deliberate nature of its approach. It wasn't attacking, it was pacing us, showing off. The excitement was now palpable, a tangible force in online forums and academic circles. Amateur astrophotographers prepared their equipment, dreaming of capturing the image of a lifetime. Planetariums rewrote their upcoming shows. The public, hearing whispers of a new great comet, began to look up once more. Hope was rekindled, pure and brilliant. Perhaps this was the one. Perhaps SWAN would succeed where Atlas had failed. Perhaps nature was giving us a second chance at witnessing true cosmic majesty. But inside the world's leading astrophysical institutions, as the first detailed scientific data began to arrive, a different emotion was taking root beneath the hope. A cold, creeping sense of unease. A chilling case of déjà vu. It began with the light curve. A light curve is the most fundamental diagnostic tool for a comet. It is a simple graph plotting the comet's brightness over time. For a healthy, stable comet, this curve should be a smooth, predictable upward arc as it gets closer to the Sun and reflects more light. When astronomers plotted SWAN's light curve, they saw the same aggressive, almost explosive rate of brightening that had been the initial harbinger of Comet Atlas's promise. The incline was steep, far steeper than models of a simple sublimating icy body would predict. This meant something else was happening. An outburst or a series of them was likely driving this rapid surge. It was exciting, yes, but it was also a warning sign. Such outbursts can signal a violently unstable nucleus, one that is fracturing and exposing vast new reservoirs of pristine ice to the sudden vaporizing heat of the Sun. It's like throwing gasoline on a fire. The result is a brilliant but often short-lived flare-up. When they placed SWAN's light curve on a graph and overlaid the data from Atlas, the two lines were almost indistinguishable. They tracked each other with an eerie, ghost-like fidelity. SWAN was following the exact same path of rapid, unstable brightening that had preceded the catastrophic disintegration of its predecessor. The next piece of the puzzle came from the spectrographs. These instruments are the master decoders of cosmic light. They take the faint incoming photons from the comet and split them into their constituent colors, a rainbow barcode. Imprinted on this spectrum are dark absorption lines and bright emission lines, which act as unique fingerprints for the chemical elements and molecules present in the comet's coma. The early spectra from SWAN were a chemist's treasure trove, but they told a deeply unsettling story. The data revealed an object that was unusually depleted in carbon. Specifically, it showed low ratios of molecules like cyanogen and diatomic carbon compounds that are typically abundant in comets originating from the Oort Cloud. A low carbon content suggests a fragile, less cohesive structure, a body made of more volatile, fluffy ices with less carbon soot to act as a binding agent holding it all together. This was the exact same chemical anomaly that had been observed in Atlas. Astronomers had theorized that this specific compositional weakness was what made Atlas unable to withstand the mounting thermal and gravitational stresses of its solar approach. Now they were seeing the very same chemical deficiency, the same fatal flaw in this new brilliant visitor. The visual evidence from high-resolution telescopes only deepened the concern. While beautiful, the coma of SWAN was not the sharp, concentrated ball of light seen around a solid, robust nucleus. Like Atlas before it, SWAN's core region appeared soft, diffuse, and elongated. It looked less like a single, coherent point of light and more like a fuzzy, overexposed smear. This morphology was highly suggestive of a nucleus that was either already in the process of breaking apart into smaller fragments, or was composed of a loosely bound rubble pile that was shedding material at an unsustainable rate. The broad fan-shaped tail and the sheer size of its hydrogen cloud spoke not of a healthy, stable object, but of one that was hemorrhaging its very substance into space with reckless abandon. It was a celestial blowtorch burning through its fuel at a furious pace, dazzling in its intensity but utterly unsustainable. The pieces were slotting into place, and the picture they formed was becoming terrifyingly clear for the scientists watching. Here was a Comet C 2020 F8 SWAN, discovered by a solar observatory on a path to flank the Earth, and promising a once-in-a-generation sky show. It was brightening at a breakneck pace, thrilling everyone who saw it, but it was doing so with the light curve of a doomed object. It was shining with the chemical signature of a fragile body. It was glowing with the morphology of an unstable core. It wasn't just similar to Atlas, it was mimicking it. It was a ghost, a perfect echo, a celestial reincarnation following the same script, act by act, scene by scene. Within the scientific community, the narrative split into two powerful conflicting currents. One was the stream of fervent, public-facing hope. Maybe this time would be different. Maybe SWAN was made of stronger stuff, a comet that could sustain this incredible output and deliver on its dazzling promise. Maybe the similarities were just a coincidence, a superficial resemblance that masked a fundamentally more resilient nature. But the other current, running deeper and quieter in the data analysis rooms and late-night academic exchanges, was one of gnawing trepidation. Professional astronomers, burned by the recent past, saw not a promise, but a premonition. They saw a cosmic tragedy about to repeat itself. They feared they were not watching the prologue to a magnificent spectacle, but the beautiful incandescent and final death throes of a comet that was already tearing itself apart. The world was looking up, filled with anticipation for a great comet, but the experts were holding their breath, wondering if they were about to witness a great collapse. SWAN was now on its final approach, a brilliant enigma flanking our world, carrying within its glowing heart both the seeds of unprecedented glory and the unmistakable omens of its own destruction. The question that consumed everyone was no longer if it would be bright, but if it would even survive long enough for us to see it. And as it raced onward, its fate inextricably linked to that of its fallen predecessor, we were forced to confront a more profound mystery. Why was this happening? Why were two comets in such quick succession appearing in our skies, only to follow the same script of brilliant self-immolation? Was this mere chance, a statistical fluke in the grand cosmic lottery, or were we witnessing evidence of something else entirely? A pattern, a hidden mechanism at work in the dark, a family of fragile comets sent tumbling our way, destined to put on a spectacular but fleeting final performance. And so the vigil began. Across our planet, a silent, coordinated network of eyes turned toward the approaching spectacle, a global community holding its collective breath. The whispers of mimicry that had haunted the edges of every conversation had grown into a deafening roar of anticipation and dread. Comet SWAN was no longer just a promising visitor. It had become a test case, a cosmic experiment playing out in real time, with the ghost of Atlas as its control group. The question was no longer times, if times it would follow its predecessor's path, but times how times closely it would hew to that tragic script. Every tick of the clock brought SWAN closer to its perihelion, that perilous gravitational hairpin turn around our star. This was its moment of maximum stress, the point of no return. Here in the sun's scorching embrace, the comet would either forge its legacy in a blaze of glory or it would break. We were about to find out which. The approach was a study in exquisite tension. Day by day, SWAN swelled in the viewfinders of both professional and amateur astronomers, its magnificent tail of ionized gas unfurling like a celestial banner millions of kilometers long. This tail, a delicate drapery painted by the solar wind, was a vibrant, almost defiant blue-green. It was the color of life, of cyanogen and diatomic carbon fluorescing under the sun's relentless glare. For a fleeting moment, you could almost believe the optimistic predictions. You could almost allow yourself to hope that this comet was different, that its constitution was stronger, that the worrisome parallels to Atlas were merely cosmic coincidence. The data streaming in seemed at first to support this hope. The light curve, the measure of its brightness, was climbing steadily, precisely as models predicted for a healthy, robust comet nucleus approaching its fiery crucible. But beneath this veneer of majestic health, the world's most powerful observatories were looking deeper, searching for the subtle tells, the almost imperceptible signs of weakness that had preceded the fall of Atlas. In the high deserts of Chile, the Very Large Telescope Array focused its 4 colossal mirrors not on the beautiful tail, but on the very heart of the comet, its nucleus. They were hunting for something specific, a telltale elongation, a slight stretching of the core that would signal the beginning of the end. Simultaneously high above the blurring effects of our atmosphere, the Hubble Space Telescope was reprogrammed its precious observation time, reallocated in an emergency override. Its mission was to capture the sharpest, most uncompromising portrait of SWAN's core, to resolve the pinprick of light into a detailed landscape of ice and rock, and to count the fragments if or when they appeared. From Hawaii's Mauna Kea, spectrographs were dissecting SWAN's light, splitting it into a rainbow of chemical fingerprints. They weren't just measuring brightness, they were analyzing its very soul. They were asking profound questions. Was the comet outgassing smoothly, releasing a steady, predictable plume of sublimating water, ice and gas? Or was it sputtering, releasing sudden, anomalous bursts of material? These bursts would be the geological death rattles of a nucleus, fracturing under stress, exposing ancient volatile ices from its interior to sunlight for the first time in 4.5 billion years. Every photon collected was a clue. Every spectral line was a potential witness to a crime scene that had not yet occurred. The scientific community was no longer just observing. They were performing a planetary-scale forensic analysis on a body that was still alive. Then came the moment, perihelion. SWAN reached its closest point to the Sun, a fiery nexus of gravitational and thermal forces. It was now bathing in energies that could sterilize worlds, enduring a celestial blowtorch that was boiling its surface at an unimaginable rate. Down here on Earth, it was just a date on a calendar, a point in an orbital diagram, but out there in the void, it was an act of brutal physical trial. For the comet's nucleus, a loose agglomeration of ice and dust barely a few kilometers across, this was a moment of profound violence. The Sun's gravity was pulling on it, not uniformly, but with a differential force, a tidal stress that sought to tear it limb from limb. The sunward side was being flash-heated, while its dark side remained in deep space cold, creating immense thermal pressures that cracked and fissured its fragile structure from within. We couldn't see this happening directly. All we could do was wait for the light from that encounter to travel across the inner solar system and fall into the waiting mirrors of our telescopes. The delay was agonizing. It was like watching a distant explosion, knowing the sound wave is coming but having no idea of its magnitude. For hours, data poured into servers at observatories and research institutions from Chile to California, from Spain to Australia. Astronomers, grad students, and technicians huddled around monitors, their faces illuminated by the eerie glow of incoming telemetry. They were running diagnostic scripts, cleaning raw image files, and stacking exposures to reduce noise, all in a frantic race against time. The first processed images from Hubble were scheduled to arrive, and in that moment the fate of SWAN would be revealed. The first file downloaded. It wasn't a photograph in the conventional sense, but a matrix of numbers, a cold digital representation of light. Software began to translate it, assigning color and contrast. Slowly an image resolved on the screen, and there was a collective intake of breath. The hope that had lingered for weeks evaporated in an instant. The image was undeniable. It was the ghost of Atlas returned. SWAN's nucleus was no longer a single sharp point of light. It was distorted, elongated, a misshapen smear against the velvet black. It looked like a drop of ink beginning to dissolve in water. It was the exact same morphology, the same celestial body language that Atlas had displayed just before its catastrophic disintegration. The mimicry was no longer a theory, it was a portrait. More images followed, confirming the first. The European Southern Observatory released its ground-based adaptive optics shots, which had pierced through Earth's atmospheric veil to achieve near space-based clarity. They showed the same horrifying picture, a nucleus under extreme duress, visibly stretching along its axis. But they revealed something more. Surrounding the main distorted core was a faint, clumpy halo of debris. These weren't the smooth, symmetrical comas of healthy comets. This was shrapnel. Small fragments, perhaps tens of meters across, had already carved off the main body. SWAN wasn't just cracking, it was actively shedding pieces of itself into space, a trail of cosmic breadcrumbs marking its own path to ruin. The comet was bleeding out before our very eyes. As the visual evidence mounted, the spectrographic teams delivered their verdict, and it was even more damning. The chemical fingerprint of the comet had changed almost overnight. The steady, predictable signature of water and cyanogen had been overwhelmed by a sudden massive spike in the spectral lines for carbon monoxide and other hypervolatile compounds. These were the materials locked deep inside the nucleus primordial ices that only see the light of day when the comet's very structure is compromised. The fissures born of thermal and gravitational stress had penetrated the comet's ancient heart. We were seeing the chemical signature of a body breaking from the inside out. The sun's heat was now reaching into its most ancient, untouched layers, causing them to flash boil into space in violent, uncontrolled jets. These jets were the source of the comet's final deceptive flourish. Paradoxically, as SWAN began to die, it flared in brightness. This death flash was a cruel trick of cosmic physics. The fragmentation exposed enormous new surface areas of pristine ice to the sun, causing a dramatic, short-lived surge in outgassing. The comet in its death throes was temporarily shining brighter than it ever had in its life. To the naked eye, if it were visible, it might have looked like a moment of triumph, but to the scientists who understood the mechanism behind it, this surge was a funeral pyre. It was the last brilliant burst of a firework before it fades into smoke and memory. They knew what came next, and it came with an inexorable certainty. Following the flare, the dimming began. The light curve which had climbed so beautifully now faltered. It plateaued, and then it began to drop. At first, it was a subtle decline, a slight deviation from the models, but it soon accelerated, becoming a precipitous plunge. The freshly exposed ice was sublimating away with incredible speed, and as it vanished, it left behind dark, inert dust and rock. The new fragments, once bright, were themselves running out of volatiles and fading from view. The comet was expending all its fuel in one final glorious and unsustainable burst. It was like a failing star shining brightest just before it collapses. The mimicry of Atlas was now complete, from the initial promising approach to the elongation, the fragmentation, the chemical outburst, the death flash, and now the final tragic fade. The frantic scramble among scientists intensified. This was no longer about prediction, it was about documentation. It was about capturing every possible piece of data from this unfolding catastrophe to understand the underlying physics. Video conferences became a constant 24-hour reality, linking teams across every time zone. An astronomer in Hawaii just finishing a long night of observations would pass the baton to a colleague in Europe who was just starting their day. The language was a torrent of data points and technical jargon, but the emotion beneath was palpable. There was awe, certainly, at witnessing such a raw display of cosmic power, but there was also a sense of scientific mourning, a sadness for the loss of what could have been. They were coroners meticulously documenting a death while simultaneously trying to understand the cause. Models were updated on the fly. Predictions for SWAN's future trajectory and brightness were being revised, not just daily but hourly. The beautiful sweeping arc it was meant to trace through our northern skies was now in doubt. Would anything be left of it? Would it be a diffuse cloud of dust, a string of faint ghostly fragments? Or would it simply vanish altogether, its constituent parts dispersing so completely that they would become undetectable, blending back into the zodiacal light from which all things in the solar system are born? The uncertainty was the new reality. SWAN had broken the contract we thought we had with it. It had promised a spectacular show and delivered a profound and unsettling mystery instead. And so the central question, the one that had been lurking in the shadows, now took center stage, illuminated by the fading light of the dying comet. The mimicry was perfect. The sequence of events was a mirror image of what had happened to Atlas. The odds of two unrelated comets arriving in the inner solar system from completely different trajectories behaving in such an identical self-destructive manner seemed astronomically small. Coincidence felt like an insufficient, almost lazy explanation. This was no longer just about one comet or even two. This was a pattern. We were now faced with a far deeper and more consequential puzzle. Were we witnessing the signature of a previously unknown class of comet, a family of exceptionally fragile ice bombs born in the same ancient distant nursery in the Oort Cloud? Perhaps they were siblings, sharing a kind of genetic flaw in their composition that made them incapable of surviving a close pass-by-the-Sunday. If so, how many more are out there masquerading as solid bodies on their way to a similar fate? Or was the explanation something different, something external? Could there be an unmapped debris field in the inner solar system, a kind of cosmic minefield that these comets were unlucky enough to pass? Through the idea seemed far-fetched, but the evidence was demanding that even outlandish theories be put on the table. As Act 3 closes, we are left staring into the abyss of this question. The tragedy of Comet SWAN is complete, but the story is far from over. Its disintegration has provided a treasure trove of data, a set of cosmic clues that point toward a much larger narrative. We set out to watch a celestial spectacle, a simple performance of gravity and light. Instead, we have stumbled into a profound detective story. The victim lies before us, its pieces scattered across the solar system. The murder weapon was the sun, but it feels as though there was an accomplice. Now, the hunt for that accomplice, for the fundamental reason behind this repeating cosmic tragedy, must begin in earnest. The ghost of Atlas has found its twin, and together their spectral light illuminates a new and unsettling darkness in our understanding of the solar system. The confirmation arrived not as a single triumphant bulletin, but as a cascade of digital whispers rippling through the global astronomical community. From Santiago to Mauna Kea, from La Palma to the automated eyes in orbit, the data streams converged on a single, unnerving truth. SWAN, at its critical midpoint, had begun to fray. The spectrographs, those meticulous dissectors of light, showed the telltale spectral lines of fragmenting silicates and sublimating ices flaring with a chaotic, unscheduled intensity. Photometry confirmed it, the comet's brightness fluctuating erratically like a dying celestial bulb. It was a ghost in the machine, a chilling echo of the fate that had befallen Comet Atlas just weeks prior. The mimicry was no longer a suspicion. It was a measured reality, an unfolding crisis playing out in terabytes of raw data. In laboratories and university departments around the world, a silent, urgent alarm was sounded. The moment of awe had passed, replaced by a frantic, all-consuming need to understand. What we were witnessing was not merely the death of a comet, but the potential discovery of a new, shared vulnerability among these ancient travelers, a fatal flaw written into their very being. The questions came in a torrent. Was this a coincidence, a case of two unrelated bodies suffering similar fates, or were we seeing the signature of a common origin, a fragile lineage of comets born in the same distant, unstable nursery of the Oort Cloud, pre-programmed to disintegrate when they felt the first true warmth of a star? The scientific apparatus of an entire planet, a vast and interconnected web of instruments and intellects, pivoted with breathtaking speed. It was as if a planetary nervous system had been shocked into action. The Very Large Telescope in Chile, its 4 colossal mirrors, typically plumbing the depths of intergalactic space, was retasked. Its adaptive optics, designed to correct for the shimmer of Earth's atmosphere, to see distant galaxies, were now focused on resolving the nascent ghostly halo of debris blooming around SWAN's nucleus. The Hubble Space Telescope, a priceless resource with a schedule booked years in advance, had its agenda scrambled through emergency override protocols. Its unblinking eye, floating high above the distortions of our world, began a series of long exposure observations attempting to capture the first definitive images of the fragments peeling away from the main body, hoping to see the children of this celestial parent before they vanished into a diffuse cloud. Radio telescopes from the sprawling plains of the Atacama Desert, to the Green Bank Observatory nestled in West Virginia strained to listen. They weren't looking for signals, but for the faint microwave emissions from hydroxyl molecules, the direct chemical descendants of water ice, a way to map the invisible plume of vapor gushing from the comet's fresh wounds. Every available asset was now pointed at this one unraveling object in the sky, turning our corner of the solar system into the most intensely scrutinized cosmic crime scene in human history. The race was on, not against a competitor, but against time itself, against the unforgiving laws of physics that were tearing our subject of study apart before we could fully comprehend it. Immediately, the theorists and modelers went to war their battleground, the glowing screens of supercomputers. Digital comets, born of pure mathematics, were subjected to the brutal conditions SWAN was now experiencing. They were bombarded with simulated solar radiation stretched by virtual gravitational fields and spun until their digital hearts burst. From this computational crucible, three primary competing narratives emerged, each with its own passionate adherents, each representing a different vision of cosmic destruction. The first and perhaps most intuitive hypothesis centered on the comet's very soul, its composition. This was the theory of the booby-trapped snowball. For the cometary geologists, SWAN and Atlas were not uniform homogeneous bodies. They were conglomerates, messy cosmic amalgams of rock dust and ices forged in the unimaginable cold of the outer solar system. Deep within this fragile structure, they argued, were pockets of extremely volatile materials, not just water ice, but frozen carbon monoxide, nitrogen, and methane. These are substances that do not merely sublimate, turn from solid to gas under the sun's influence. They flash boil with explosive force. Imagine a champagne bottle left in the sun, not for an hour, but for 4.5 billion years, its internal pressure building in the silent cold. As SWAN approached the sun, the warmth penetrated its outer insulating layers of dust. It was a slow, creeping heat that finally reached one of these deeply buried pockets of hypervolatile ice. The result would not be a gentle hiss of gas, but a violent, concussive detonation from within. This subterranean explosion would be powerful enough to fracture the entire nucleus, creating deep fissures and shearing off massive fragments. It would be a self-inflicted wound, a geological time bomb finally going off. This theory was compelling because it elegantly explained the mimicry. If both SWAN and Atlas were born from the same parent body, a colossal ancient comet that shattered millennia ago, they could be siblings sharing the same flawed genetic makeup. They would carry the same unstable chemical pockets, destined to detonate at roughly the same distance from the Sun at the same point in their orbital journey. They were, in effect, ticking bombs built to the same design specification, and we were simply witnessing their synchronized demolition. The hunt was now on for the chemical fingerprints of this explosion, for the unique spectral signatures of carbon monoxide or other supervolatiles in the expanding coma, the smoking gun that could prove this theory of internal sabotage. But another camp of scientists looked not inward but outward for the assassin. For them, the comet was not a suicide bomber, it was a victim. They pointed the finger directly at our own star. The Sun, the source of all life in our solar system, is also a profoundly violent and chaotic entity. It constantly spews a torrent of charged particles into space, known as the solar wind, a relentless supersonic storm that travels at over 1 million miles per hour. While our planet is protected by its robust magnetic field, a tiny fragile comet has no such defense. To the solar physicists, SWAN's nucleus was a mountainside being eroded by a perpetual hurricane. This solar wind, they argued, acts like a relentless celestial sandblaster, stripping away the comet's protective outer layers particle by particle, hour by hour. This process could progressively weaken the comet's structure, exposing more volatile ices beneath the surface and accelerating its decay. Yet the solar wind alone might not be enough to explain the sudden catastrophic fragmentation. For that, they invoked a far more powerful weapon from the Sun's arsenal, the coronal mass ejection, or CME. A CME is a cataclysmic event, a solar eruption that hurls billions of tons of magnetized plasma into space at staggering speeds. If a comet like SWAN were unlucky enough to be in the direct path of one of these plasma sledgehammers, the consequences would be devastating. The impact would deliver a colossal shockwave of energy and momentum capable of shattering the nucleus outright, or at the very least, triggering the kind of internal detonations the geologists proposed. The challenge for this theory was timing. It required an element of terrible luck, a cosmic wrong place at the wrong time scenario. Investigators began poring over data from solar observatories like the Solar Dynamics Observatory and SOHO, searching for evidence of a CME eruption that was aimed in SWAN's direction at the precise moment its troubles began. Was there a kill shot from the Sun that we missed? Could both Atlas and SWAN have been blindsided by unseen solar outbursts, their shared fate not a matter of heredity but of pure, brutal cosmic chance? The solar system in this view was not a predictable clockwork machine, but a shooting gallery, and these comets were simply two unlucky targets that wandered into the line of fire. It was an unsettling thought, suggesting a level of random violence that made predicting the future of any comet an exercise in probability rather than certainty. The third major hypothesis was perhaps the most elegant, the most subtle, and the most chilling. It involved no explosions from within, no violent impacts from without. Its weapon was silent, invisible, and inescapable. Its weapon was gravity. The astrodynamicists, masters of celestial mechanics, saw the comet's demise not as a single event, but as a slow and agonizing execution by torture. As SWAN plunged deeper into the solar system, it fell into the Sun's immense gravitational well. But this pull is not uniform. The side of the comet closer to the Sun feels a slightly stronger pull than the side farther away. This differential is known as a tidal force, the same force that governs the oceans on Earth. For a small, loosely held together body like a comet, this constant stretching and squeezing is a form of relentless torture. Imagine holding a fragile ball of dried mud and constantly gently pulling on opposite sides. For a time, nothing would happen, but slowly microfractures would form deep within its structure. They would lengthen, connect, and propagate. The body would be weakening from the inside out, its structural integrity being silently compromised. According to this theory, the comet's rotation would exacerbate the problem. Each spin would introduce new stresses, flexing and twisting the already weakened nucleus, much like bending a paperclip back and forth. The comet essentially becomes its own gravitational gyroscope, but one that is being constantly torqued and warped by the Sun's influence. At a certain critical distance from the Sun, the midpoint where we saw the disintegration begin, the accumulated stress would finally exceed the comet's tensile strength. It wouldn't explode, it would simply crumble. It would surrender to the inexorable pull of gravity, falling apart in a quiet, almost graceful surrender. This hypothesis was deeply compelling because it required no special circumstances, no volatile pockets, no well-aimed solar flares. It was a fundamental consequence of physics. It implied that any comet of a certain size, mass, and composition, following a similar trajectory, would be doomed to the same fate. The mimicry of Atlas and SWAN would be in this view the inevitable outcome of a shared structural flaw being exploited by the fundamental laws of the universe. They were simply not built to survive the gravitational strains of a close solar pass, and their synchronized deaths were a stark demonstration of that innate weakness. This schism in the scientific community created a palpable tension, a high-stakes intellectual drama playing out in real time across secure video conferences and encrypted forums. On one screen, you would have a geologist presenting a detailed chemical model of sublimating gases pointing to a subtle spike in the latest spectral data from Hawaii as proof of their detonation theory. On another, a solar physicist would display a magnetohydrodynamic simulation showing a plasma wave impacting a virtual comet, arguing that the timing perfectly matched the initial brightening observed by European ground stations. Moments later, an orbital dynamicist would counter with a refined gravitational model demonstrating how tidal stresses would peak exactly where the fragmentation began, rendering all other explanations needlessly complex. These were not abstract academic debates. The models they built and the theories they championed had immediate practical consequences. Each hypothesis predicted a different future for SWAN, a different pattern of fragmentation, and a different kind of spectacle for us back on Earth. If the geologists were right, the fragmentation might be a one-off event, a single large explosion, followed by a period of relative stability, as the remaining more solid portion of the nucleus continued its journey. The show might yet go on, albeit with a slightly dimmer leading actor. If the solar physicists' theory of erosion and impacts held true, the comet's fate would depend entirely on the sun's mood. It could stabilize if it entered a quiet patch of space, or it could be blasted into oblivion if another CME happened to be heading its way. Its future was unpredictable, a hostage to solar weather. But if the gravitational stress model was correct, the outlook was far more grim. The process would be relentless. The initial fragmentation was not the end, but the beginning of a cascade. The larger fragments would themselves be subjected to the same tidal forces, breaking into smaller pieces, which would then break into even smaller ones until the entire comet unraveled into a diffuse river of dust and ice. The intense, focused debate was therefore a race to forecast the immediate future, to tell a waiting world what to expect next from this celestial visitor. And so our expectations had to be revised. The promise of a brilliant star-like object, a great comet arcing magnificently across the pre-dawn sky, began to fade, replaced by a more ethereal and perhaps more poignant reality. Professional and amateur astronomers alike were now being told to look not for a sharp, dazzling point of light, but for a ghostly smear, a diffuse streak of cosmic chalk. The comet was becoming a phantom of its former self. As the nucleus continued to shed material, the once condensed coma of gas and dust expanded into a vast translucent cloud, many times larger than the planet Jupiter, yet so tenuous that starlight could easily pass through it. The beautiful, well-defined tails, one of dust and one of ions, were becoming blurred and indistinct, a tangled mess of debris rather than a graceful cosmic banner. We were witnessing a transition from a singular majestic object into a sprawling, haunting memorial to what it once was. There is a unique and melancholic beauty in this. We were not just seeing a comet, we were watching the birth of a meteor stream. Every particle of dust, every shard of ice being shed by SWAN, was now entering its own independent orbit around the Sunday. These fragments, this celestial shrapnel, would continue to travel along the comet's path for millennia to come. In the distant future, long after the last recognizable piece of SWAN has vanished, Earth may one day drift through this river of debris. On that future night, our descendants might look up to see a spectacular unknown meteor shower, a sudden flurry of shooting stars. They would be seeing the final glittering embers of Comet R2 SWAN, a final farewell written in fleeting lines of light across the sky. But for now, our view is of the immediate aftermath of the deconstruction itself. The show has changed. It is no longer a drama of brilliant arrival, but a somber, silent epic of dissolution. Yet, in its own way, it is just as captivating. For what we are learning from this shared death, this synchronized failure of two cosmic travelers, is rewriting our understanding of what comets are. They are not the simple, inert snowballs we once imagined, but complex, fragile, and deeply vulnerable worlds. And with every new piece of data, every image of its unraveling core, SWAN is giving us one last spectacular gift, a front-row seat to the beautiful, inexorable, and messy process of creation and decay that governs our entire universe. The investigation into the fragments, however, was just beginning, and what we would find within that expanding cloud of debris would raise even more profound questions about our own place in this cosmic story. And so the vigil begins. Across the globe, a planet holds its breath, its gaze turned upward. In the silent, cold domes of professional observatories, colossal mirrors polished to near perfection pivot with silent hydraulic grace. They are aligning with a single fleeting coordinate in the celestial sphere, a point of hope and apprehension. In backyards and on remote hilltops, a devoted army of amateurs huddles around their own instruments, their breath misting in the chill of the pre-dawn air. For weeks they have tracked this emerald pilgrim, this ghostly voyager named SWAN, charting its every surge and tremor. They have watched it follow the spectral footprints of its fallen predecessor Atlas, and now tonight, its own moment of truth has arrived. The night of its closest approach to Earth, the crescendo of its flanking maneuver is upon us. This is the final performance, the last chance to answer the question that has echoed through the astronomical community for months. Will we witness a glorious celestial spectacle, or the final fading whisper of a dying comet? The initial reports flicker across computer screens in darkened control. rooms a staccato pulse of data from a world united in observation. From the clear, high-altitude skies of the Atacama Desert to the seasoned observatories of Arizona and the Canary Islands, the first light is being gathered. The initial word is not one of explosive triumph, but of quiet, strained searching. Telescopes that were expected to be filled with a magnificent, sprawling coma are instead showing something else, something more subtle, more ethereal. The first images that materialize are ghostly indistinct. Where astronomers had hoped for a vibrant, well-defined nucleus, a brilliant point of light driving a magnificent tail, they find only a diffuse, melancholic haze. It is there, but only just. A smudge of eerie green against the velvet black, a phantom that refuses to fully resolve. For the amateur observer peering through the eyepiece of a 10-inch reflector, the feeling is one of profound, creeping disappointment. You had followed the charts, calculated the precise moment it would clear the horizon, your heart pounding with the promise of seeing a true naked-eye wonder. The stories of Hale-Bopp and Hyakutake, those titans of the cometary world, danced in your memory. You expected more. Instead, what you find is a challenge, a test of your observing skill. Averted vision is required, looking slightly away to allow the more sensitive rods in your eye to catch the faint luminescence. It's a familiar technique for spotting faint nebulae, not for what was billed as the comet of the year. The brilliant emerald head, so vivid in long exposure photographs from weeks prior, now appears, washed out a pale mint green at best. The magnificent ion tail, that delicate streamer of charged particles sculpted by the solar wind, is a ragged, fragmented wisp. The broader dust tail, which should be fanning out like a celestial peacock's plume, is nearly invisible, a spectral hint of what might have been. This is not the triumphant crescendo we were promised. This is a diminuendo, a slow, heartbreaking fade to silence. As the hours of the night wear on, the consensus becomes undeniable, spreading through online forums and scientific bulletins like a somber wave. From Perth to Pennsylvania, the story is the same. Comet SWAN is not putting on a show. It is putting on a clinic in cometary disintegration. The mimicry of Atlas is no longer just a curious parallel. It has become a tragic, undeniable prophecy fulfilled. The comet has followed the script of its predecessor down to the final, agonizing scene. It has arrived on stage for its grand finale, only to collapse before the audience's eyes. The brilliant actor has forgotten its lines, its voice reduced to a hoarse whisper. The flanking maneuver, which was meant to be a triumphal flyby, a close pass for all the world to admire, has instead given us a front-row seat to a cosmic demise. We are not spectators at a celestial pageant. We are mourners at a wake. But why? Why this slow, agonizing dissolution? The answer scientists now realize with chilling certainty was encoded in SWAN's very being from the moment it was born, billions of years ago in the frigid darkness of the Oort Cloud. To understand its failure, we must abandon the simple, reassuring image of a comet as a solid, monolithic, dirty snowball. That analogy, while useful, hides a universe of complexity. Not all comets are created equal. Some, like the famed Halley's Comet, possess a dense, consolidated nucleus, a robust core of ice and rock forged under immense pressure in the protoplanetary disk. They are the veterans of the solar system, capable of surviving hundreds of passages around the sun, their surfaces evolving into a tough protective crust. They are the celestial mountains, weathered but enduring. Then there are the others, the fragile ones, the rubble piles. Imagine not a solid snowball, but a loose collection of icy pebbles and dust held together by little more than their own feeble gravity and frozen primordial gases. They are not cosmic mountains. They are cosmic sandcastles, exquisite in their temporary structure, but profoundly vulnerable. These comets are not built for the rigors of the inner solar system. The journey from the deep freeze of interstellar space is a brutal assault on their delicate architecture. For SWAN, like Atlas before it, this was its very first voyage inward, a pristine, untested traveller facing the full fury of the sun for the first time. It possessed no hardened crust, no veteran's resilience. It was, in essence, a celestial newborn thrown into a furnace. As it plunged closer to the sun, the gentle warmth that first woke it from its slumber became a relentless, overwhelming blowtorch. The process of sublimation ice turning directly into gas, did not just occur on a single solid surface. It happened everywhere throughout its porous, loosely bound structure. Countless jets of gas erupted not from a unified core, but from innumerable small icy bodies within the larger agglomeration. This wasn't a powerful directional engine propelling the comet forward. It was a chaotic, self-destructive force, tearing it apart from the inside out. Each jet of gas acted like a tiny rocket pushing one fragment away from another, slowly and inexorably loosening the gravitational bonds that held the whole fragile structure together. The comet wasn't exploding in a single violent burst. It was unraveling. It was dissolving. We were witnessing a symphony of silent decay, a graceful but terminal process of disintegration played out over millions of kilometers. The high-resolution data pouring in from the world's premier telescopes confirmed this diagnosis with devastating clarity. The Hubble Space Telescope, tasked with performing a celestial autopsy, returned images that settled the matter for good. Where a single sharp point of light should have been, Hubble saw something entirely different. A ghostly, elongated shroud of gas and dust, and within that shroud not one nucleus but a cascade of smaller, fainter fragments. A string of dying embers, each one a piece of the original heart of SWAN, now drifting apart on slightly different orbits. It was the smoking gun. The comet had fractured likely weeks ago, and what we were seeing during its closest approach was not the comet itself, but its funeral procession. The green glow we had so admired was not the sign of a healthy, active nucleus. It was the comet's lifeblood, its reserves of diatomic carbon and cyanogen bleeding out into space from 1,000 mortal wounds. The great apparition was in fact a ghost. This fragmentation provides the ultimate key to understanding the mimicry of Comet Atlas. Astronomers now believe that both comets were likely born from the same parent body, a much larger object that shattered in the distant past, creating a family of structurally weak rubble pile siblings. They were twins not in orbit, but in composition and fragility. When Atlas made its inaugural journey, it followed this preordained path of disintegration. A year later, its sibling SWAN was dispatched from the Oort Cloud on a similar trajectory destined to suffer the exact same fate. We were not just witnessing a coincidence, we were observing a shared genetic flaw, a hereditary weakness playing out on a cosmic scale. The path of mimicry was not a choice, but an inevitability written into their very ice and dust. They were born to fail their brief, brilliant lives, merely a prelude to their spectacular and scientifically priceless dissolution. The geometry of the flanking pass itself added a final, poignant layer of irony to SWAN's story. The comet's trajectory brought it relatively close to Earth in astronomical terms, about 85 million kilometers, or just over half the distance to the Sunday. This proximity should have guaranteed a spectacular view, yet the orbital mechanics worked against us. From the perspective of the Northern Hemisphere, where the majority of large observatories and amateur astronomers reside, SWAN remained frustratingly low on the horizon, perpetually battling the encroaching glow of twilight. It was a celestial chase scene where the quarry never truly broke free into the clear, dark expanse of the night sky. Even if the comet had held together, even if it had been as bright as the most optimistic predictions, its position would have made it a challenging, fleeting target. It was as if the universe had conspired to grant us a close look, only to draw a thin veil of atmospheric haze and twilight across the view at the last possible moment. This challenging viewing angle, however, proved to be a scientific blessing in disguise. The specific geometry of the Sun, Earth, and Comet SWAN during the flyby created a phenomenon known as forward scattering. As SWAN passed between Earth and the Sun, the dust particles in its tail were illuminated from behind. This backlit view is incredibly sensitive to very fine, small dust particles, the kind of primordial dust that is blown off during the early, gentle stages of a comet's activity. For a brief period, even as the nucleus was visibly fading, the dust tail experienced a temporary illusory brightening. It was a phantom limb of dust and gas, a glowing memory of the comet that once was. This subtle effect, captured by dedicated photometers and spacecraft like NASA's Stereo mission, provided invaluable data on the composition and size of the dust grains that formed the building blocks of our solar system 4.6 billion years ago. SWAN, in its death throes, was offering up its own primordial essence for our analysis, a final generous gift from a dying visitor. From the control rooms of the Solar and Heliospheric Observatory, or SOHO, which has watched countless comets meet their fiery end as they plunge into the sun, SWAN's journey offered a different kind of drama. SOHO's coronagraphs, which create a perpetual artificial eclipse to study the sun's faint outer atmosphere, watched as the skeletal remains of the comet entered their field of view. The images were stark and unequivocal. Gone was the bright condensed head. In its place was a long, impossibly faint streak of material, a smear of dust so diffuse it was barely distinguishable from the background solar wind. It was the wreckage field of a cosmic shipwreck, its cargo of ancient ice and dust now scattered and adrift, destined to slowly dissipate and become a vanishingly thin ring of debris around the Sunday. The comet that had captivated a planet had been reduced to a trail of cosmic dust, its grand journey ending not with a bang, but with a final silent dispersal into the solar wind. So, what have we learned from this beautiful, heartbreaking failure? We learned that the Oort Cloud, that vast, mysterious reservoir of comets at the edge of our solar system, is not populated solely by resilient, rocky icebergs. It is also home to these fragile, loosely bound collections of primordial fluff objects that cannot survive their first encounter with the sun's warmth. SWAN and Atlas have given us a new category of celestial object to consider: the disrupting or ephemeral comet. Their dramatic fizzles are a powerful reminder that for every great comet that graces our skies, countless others may begin the long fall inward, only to perish in anonymity. Their journey cut short before they can ever become a spectacle for our world. They are the fallen soldiers in the sun's great gravitational war, their stories untold. The failure of SWAN also served as a crucial, humbling lesson in the science of prediction. Our models for forecasting cometary brightness are still in their infancy, based largely on the behavior of repeating, well-understood comets. These pristine first-time visitors from the Oort Cloud play by an entirely different set of rules. Their brightness can surge unexpectedly as fresh pockets of ice are exposed to sunlight, leading to wild overestimates of their potential, only to plummet just as dramatically when their fragile structure gives way. SWAN, with its dramatic flare-ups and subsequent collapse, has provided a wealth of data that will be used to refine these models for decades to come. Its ghost will haunt the equations and algorithms of future astronomers, a constant reminder of the wild, unpredictable nature of these celestial visitors. We failed to predict its demise, but in that failure we gained the knowledge to better understand the next one. We did not get the dazzling display we had hoped for. There will be no timeless photographs of SWAN hanging like a lantern over a moonlit landscape. There will be no stories passed down to our children of the great comet of 2020 that lit up the night sky. What we received instead was something arguably more profound, a rare and intimate window into the processes of creation and destruction that shape our solar system. We witnessed the death of an object that had remained untouched and unchanged for billions of years. We saw its ancient heart, forged in the same nebular cloud that gave birth to Earth, break apart and release its primordial secrets into the light. SWAN's flanking maneuver was not a failure of a performance, but a final, selfless act of scientific revelation. Its light has now faded from our view, its fragmented body continuing on a path of no return, a ghost ship sailing an empty solar sea. But its legacy, written in the language of physics and light, is now permanently etched into our understanding of the cosmos. The emerald apparition is gone, but the lessons it taught us will shine on, illuminating the path for future discovery. Its silent, fading whisper has told us more than the loudest celestial roar ever could, leaving us with a new and more complex appreciation for the fragile beauty of these cosmic travelers. SWAN's ghost now haunts the inner solar system, its dust a faint memory of its brief, brilliant passage. It leaves behind a crucial question, a new mystery to solve: how many more of its fragile brethren are out there dormant in the deep dark, waiting to begin a journey they are not destined to complete? In the silent aftermath, where two brilliant cosmic hopes once blazed, there is now only a widening river of dust and gas. The twin sagas of Atlas and SWAN have reached their quiet, inevitable conclusions, not with a climactic flourish against the canvas of the inner solar system, but with a final, dignified surrender to the forces that both created and destroyed them. They are gone. Their light, which travelled for millions of years from the dark frontier to grace our skies, has been extinguished. What they leave behind is not a void, but a profound and unsettling echo, a question whispered across the vacuum of space that has fundamentally altered our relationship with these celestial nomads. For all their fleeting brilliance, their true legacy was never about the spectacle they promised, but about the startling, almost unnerving symmetry of their shared fate. It was a story written in disappearing ink, forcing us to read between the lines of cosmic history itself. We watched, captivated, as they followed one another from the deep, dark two strangers on the same path, their behaviour a near-perfect reflection in a celestial mirror. One moment they were titans, growing brighter with each passing day, promising a generational light show. The next they were ghosts, their solid cores dissolving into ethereal shrouds of their former selves. This mimicking was more than a coincidence. It was a revelation. It suggests that the grand, lonely journey from the Oort Cloud is perhaps a far more standardized and far more perilous ordeal than we ever imagined. It implies the existence of a specific class of comet, a fragile archetype born in the same primordial crucible, destined to meet the same fiery end upon their very first encounter with the sun's intense proximity. Atlas and SWAN were not anomalies. They were emissaries from this unseen population. Their dual disintegration, a stark message about the true nature of these icy pilgrims. They have forced us to redraw the map of cometary evolution, to account for a pathway that leads not to a triumphant swing around the sun, but to a dramatic, radiant act of self-destruction. Their synchronized demise became a unique cosmic laboratory, an unprecedented opportunity to perform a celestial autopsy on two nearly identical subjects. From the light curves, the sudden surges and subsequent fades, we learned about the volatile materials churning within their hearts. These were not solid rocky snowballs, but loose fluffy aggregates, barely held together by their own feeble gravity. They were likely rich in super-volatile ices, like frozen carbon monoxide and nitrogen materials, that turn to gas at incredibly low temperatures, far out in the solar system's colder suburbs. As they plunged inward, the gentle warmth of the sun was not a nurturing force but a trigger, initiating a runaway sublimation process from deep within their cores. Think of it not as a simple melting, but as a deep internal fracturing, the very structure of the comet tearing itself apart from the inside out. Their spectacular brightening was not a sign of strength, but the scream of their impending dissolution. They were, in essence, cosmic dynamite, their long, slow fall toward the sun simply the lighting of an ancient fuse. The shrapnel from these explosions, the spectral fingerprints left in their expanding comas, told us even more. We saw the chemical signatures of organic molecules, the complex carbon-based compounds that are the fundamental building blocks of life. These weren't just sterile chunks of ice. They were reservoirs of creation carrying the precious cargo of our own origins. Their disintegration, tragic as it seemed, was also an act of cosmic seeding, scattering these vital ingredients into the plane of the solar system. It is a powerful reminder that the universe operates on scales of creation and destruction that dwarf our human perspective. The death of a comet might be the birth of a billion possibilities on a distant, nascent world. Through the twin lenses of Atlas and SWAN, we glimpsed the raw, unrefined material from which our planets, our oceans, and ultimately we ourselves were forged some 4.5 billion years ago. They were time capsules that shattered upon delivery, spilling their ancient secrets for us to painstakingly piece back together. And yet this entire saga delivered a powerful and necessary lesson in humility. In an age of precision astronomy, where we can map the surfaces of distant worlds and listen to the gravitational whispers of colliding black holes, two relatively simple comets completely defied our most sophisticated predictions. We, the confident observers, charted their paths, calculated their brightness, and told the world to look up, and we were wrong. This failure is not a weakness of the scientific method, it is its greatest strength. It reveals the boundaries of our knowledge, the edges of the map where the dragons of the unknown still lie. The universe is not a perfectly predictable machine, and comets, these wild cards of the solar system, are its most potent reminders of that truth. They are governed by a chaotic interplay of solar radiation, gravitational tides, and internal pressures that we are only just beginning to model. Each new comet is a new test, a new pop quiz from the cosmos, and the identical failing grades we received on Atlas and SWAN have spurred a revolution in our thinking, forcing us to build better models, to ask smarter questions, and to embrace the profound beauty of uncertainty. This newfound understanding, born from the dust of two dead comets, is already shaping the future of our celestial explorations. The hunt is evolving. We stand on the cusp of a new golden age of discovery, spearheaded by sentinels like the Vera C. Rubin Observatory in Chile. This is not just another telescope, it is a digital eye of unprecedented scale, designed to scan the entire visible sky every few nights. Where we once discovered dozens of comets a year, Rubin will discover thousands. It will generate a motion picture of the night sky, a flowing, living tapestry of the cosmos, in which faint inbound travelers from the Oort Cloud will appear as steady, undeniable streaks. It will not just find comets, it will find them earlier, farther out, giving us years, not months, to study their approach. It will build a vast statistical library of cometary behavior, allowing us to finally see if the fragile, self-destructing nature of Atlas and SWAN is the exception or the rule. We will move from telling individual biographies to writing a comprehensive census of these primordial objects, understanding the full diversity of their composition and their fate. But seeing from afar is no longer enough. The ghosts of Atlas and SWAN have intensified our desire to get closer to touch and taste these messengers from the past. The future of cometary science lies in interception, in missions that are as agile and unpredictable as their targets. Imagine a spacecraft not aimed at a known destination but parked in the void waiting. A silent, patient predator of knowledge hibernating at a stable point in space awaiting the call. This is the audacious concept behind the European Space Agency's Comet Interceptor mission. It will wait for the Vera Rubin Observatory or another survey to spot a brand new comet, a pristine visitor straight from the Oort Cloud, one that has never before passed through the inner solar system. Once the target is identified, the interceptor will awaken, firing its thrusters to embark on a high-speed chase, a cosmic ambush designed to meet this untouched relic head-on. It will be humanity's first encounter with a truly fresh piece of the solar system's original building material, a body that has not been baked, altered, or stripped of its most volatile secrets by repeated solar passages. This mission and others like it will carry suites of instruments that are the direct descendants of the lessons we learned from our two failed stars. They will carry high-resolution images to map the fracturing surfaces, searching for the active vents that signal an impending breakup. They will have mass spectrometers to sniff the outgassing coma, providing a detailed chemical inventory and searching for the subtle organic signatures that tell the story of prebiotic chemistry. Some concepts even envision impactors or subsurface probes designed to pierce the outer crust and analyze the ancient, undisturbed layers beneath. We are no longer content to simply watch comets die. We want to understand the precise mechanisms of their lives, to read the full story chapter by chapter, from their quiet genesis in the cold dark to their final incandescent moments in the solar furnace. We are building the tools to move beyond prediction and into the realm of direct empirical understanding, to finally grasp the physical reality behind the ethereal beauty. And so, as we look to the heavens, we do so with a new kind of vision. The sky is no longer just a static backdrop of distant stars. It is a dynamic arena, a place of constant change of arrivals and departures. The tales of Atlas and SWAN have been woven into the fabric of our cosmic awareness, a cautionary tale and a source of inspiration in equal measure. They taught us that even the most promising celestial journeys can end in dissolution, and that the universe holds its deepest secrets in the most fragile of containers. They reminded us that our quest for knowledge is not a simple linear march toward enlightenment, but a complex dance with an ever-surprising partner, a dance of observation, prediction, failure, and renewed discovery. The disappointment of their fading was real, a shared global moment of anticlimax. But what rose from those ashes is something far more valuable, far more enduring, a deeper respect for the wild, untamable nature of the cosmos, and a hardened resolve to pursue its mysteries with even greater vigor. The next great comet is already out there. It is falling toward us now, a silent, frozen world on a journey of 1,000,000 years, completely unaware of the tiny, curious planet that lies in its path. We do not know its name. We do not know its composition. We do not know if it is a resilient, rocky survivor, destined to dazzle our descendants for generations, or another fragile phantom fated to offer up its secrets in a final, brilliant act of disintegration. But we will be watching, with new eyes, new tools, and the hard-won wisdom gifted to us by the celestial twins who came before. The individual comets may be ephemeral, their paths unpredictable, their fates uncertain. But the human drive to understand, to reach out into the vast, silent darkness and find our own origin story written in the heart of a falling star, that relentless pursuit of cosmic knowledge that we have learned is truly steadfast. It is the most powerful, inexorable force of all.